let us conclude with this third example, even if in the following lesson I shall show you a particular, very interesting particular case. However, for the moment, let us remain on the general. We can represent the result we have obtained a moment ago in the following manner. Consider an Azure box, but note this Azure box regards produced goods. So on the axis of this Azure box there are the quantities of factor 1 and factor 2 employed in the production of good 1, and analogously the quantities of factor 1 and factor 2 employed in the production of good 2. Is it clear? The interpretation of the box is the same, of the consumption box, of course. The length of this basis represents the total available quantity of good of factor 1, while the length of this height represents the total available quantity of factor 2. The interpretation of these magnitudes changes, but from an analytical point of view is the same thing as before. As before, we can consider an allocation like this x, which is inefficient, because it is possible by passing to x prime to increase both levels of production. Exactly as before, when passing from x to x prime implied an increase in both levels of utility, in this case, of production. These are isoquants and not indifferent schools or codes. On the contrary, this particular allocation x cap is a Pareto optimum for the production. That tells you it's not possible to find another allocation of factors which not decreases, does not decrease any level of production and increase at least one level of production, as before. It's a Pareto optimum of production. Also, in this case, we have a Pareto set, as before, the set of all Pareto optima. By means of this Azure box, we can build another graphic. On the axis of this graphic are the produced quantities of two goods, 1 and 2. The products, substantially. Well, take any allocation of factors. Look at the levels of the two isoquants which pass by x. Levels Q1 for the first good, Q2 for the second good. And report these levels of production on this graphic. You obtain the pair of level of production you obtain if you allocate the total quantities factor according to the allocation x. Well, you can repeat this procedure for every allocation x in the Azure box. we obtain a set, which we'll name T, of all the possible pairs of good 1 and good 2, which can be obtained by allocating in every way the available quantities of factors between our two production sectors. You obtain this set T. Question, but if you consider a Pareto optimum like X cap, where is the corresponding point on this graph? Clearly on the boundary. You have here Q cap 1, Q cap 2, which has the quantities produced by the economy when you allocate the total available quantities of factors in the way given by this point X cap. So, all the points on this boundary represent, correspond to Pareto optima in the edge box. Word no result. This is the so-called production frontier. Or transformation function. Clearly, it's not that good 2 is transformed in good 1 or vice versa. Simply, a part of the factors which were employed in the production of good 2 are transferred to the production of good 1. So the production of good 2 decreases, while the production of good 1 increases. We proved a moment ago, not very rigorously, afterwards I shall prove in a rigorous way all this theorem in a more general context of course. However, we proved a moment ago that in the equilibrium of economy, the total value of production is maximized. Let us report this result in this graphic. We can write simply the total value of production in this way. As usual, if I posit this total value of products equal to any constant C, say, I obtain well-known iso-revenue straight line, which can be rewritten in this standard way. Is a straight line. The locus of all the points such that the total value of production is equal to the given constant. Clearly, there are many of these iso-revenue straight lines, one for each constant. So you have a result like this. The slope of all these iso-revenue straight lines is equal because it's nothing but the ratio between prices with changed sign. But according to our previous theorem, in equilibrium, the total value of production is maximized. Can be proved that the solution of the maximal problem, as I told you, is equivalent to that of determining the equilibrium allocation in a pure competitive economy. So the point which represent the quantity produced in equilibrium must belong to the highest isorevenue straight line, which has an intersection with the set T. Is it clear? It is obvious, as this graphic shows, that the pair Q star 1 and Q star 2 of the quantities produced in equilibrium is the consequence of a Pareto optimum in the allocation of factors. Because if ab absurdo the quantity produced in equilibrium were below the transformation curve, as in this case, you, by definition, can increase the quantity of both goods, or at least the quantity of one good, while the other quantity remains unchanged, remaining in the set T. But if all prices are positive, this alternative pair of quantities will give a greater value than the quantities produced in equilibrium. And this contradicts our previous result. So, the pair of quantities which are produced in equilibrium must lie on the production frontier. Or the transformation function, use the term which you wish. And this means, obviously, that in equilibrium, also for production, there is efficiency. In other terms, the equilibrium allocation of factors must be a Pareto optimum for production, because this pair belongs to the frontier of a set T. This is a very important result. In other terms, general economic equilibrium implies not only a consumption Pareto optimum, so to speak, but also a productive Pareto optimum, a technological Pareto optimum. There is efficiency both in consumption and in production. So, the situation in the Angel box is the following. The equilibrium allocation of production factors must correspond to a Pareto optimum of production, and therefore, note, will be a point like this. This is the factor allocation which determines the quantity Q star 1 and Q star 2 which are produced in equilibrium. And it is a Pareto optimum. Last step, if these the production functions are differentiable, these isopoints will be tangents. And see, by well-known result, the marginal rate of substitution between two factors must be equal to the ratio of factor prices, another well-known result of production theory. You have that since there is only one tangent to both these isopoints, also the ratio of W1 on W2 is uniquely determined, as I told you before. In reality, also the exact values of W1 and W2 are uniquely determined, not only their ratio. This is a very important result. As I told you a moment ago, the factor prices, the equilibrium factor prices are uniquely determined by the international product prices, in this way. Well, this is the typical model of an open economy with given product prices and factor prices which are determined on the internal markets of the country, since factors are not movable between different countries. It remains to analyze a very particular case, the case in which every production function presents constant returns to scale. You remember, constant returns to scale means that when you multiply all factors by the same constant, positive constant, production increases in the same proportion. You redouble all the factors, also production redoubles. In this case, it can be proved that the transformation function is concave as this form. Oh, sorry. Q1, Q2. Or only in the particular case in which the Pareto set is linear, as a linear form likewise. But however, the case in which the Pareto set is linear, in other terms, it is the segment which unites O1 to O2, is very, very difficult to imagine in the reality. So the case will be of a concave production frontier. If you assume constant returns to scale, you can prove many other interesting results. The so-called Aksherulin theorem, the so-called Rybczynski theorem, the so-called Stolper-Samuelson theorem, which are mainly employed in international trade theory, but which maintain their economic meaning also in a closed economy. But for today, stop. We shall examine this particular case next week, and then we shall begin the analysis of a rigorous theory of general equilibrium. Because up to this point, I limited myself to illustrate without rigor the main result of the theory.